The first thing what I do is usually there is a good website known as typeset.io. So this is for summarizing these scientific papers. So in here what you can do is you can see there are a lot of things in my library over here. So I'll just create, let's suppose, one more folder. Let's call this LLMs, and this LLMs I'll upload this. So I'll upload this research paper, DeepSeek R1. Okay, so this is the paper. Okay, so the first question I usually ask is, because I don't go on, I ask for the outline. Give me the outline of the paper and each heading with a little summary. So I get a what's called as that peaked vision, at least what is going on. So this actually gave me this outline of the paper. So usually what I do is I'll copy whole of this. Okay, so after that I usually open Notion, which I'll now do online. This is Motion. So I'll log in. It should allow me to log in. I have IIC mail ID here. So here if you see, there are a lot of these things. I was reading some paper also here. This is a paper I was recently reading on biology. So I will have a folder here somewhere. Let's add one more folder for these LLMs. So here I'll add LLMs. So here I'll add a page. If it is not visible, do let me know. I'll just zoom it then. So this is DeepSeek R1. So I'll paste the outline. Okay. Are you following? Any questions? Do stop me.
Yes, we are following.
So now what I'll do is I'll go through this first. I'll see the outline. So in the outline, what I can see is introduction, and the introduction discusses the advancement in reasoning capabilities of large language models, particularly highlighting OpenAI's O1 series models and their chain of thought COT process. It addresses the ongoing challenges in effective test time scaling and the limitations of the previous models in achieving comparable reasoning performance to this O1 series. This section outlines the strategic employed to create cold start for DeepSeek R1. Actually this introduction looks quite a hallucination to me, क्योंकि शायद इसके बारे में बात नहीं हो रही. So what I can do is I can go here, first read the abstract. So here we introduce our first generation reasoning models. So DeepSeek R10 and DeepSeek R10F model trained by large scale reinforcement learning without proper supervised fine tuning as preliminary step. So let me clarify some things here so that you also follow, because a lot of things are going in my head. So I'll tell you what things are going in my head when I read this stuff. So the first thing is you should know a bit about language models. So I'll start from there so that you also follow. If I read it, you also follow similarly. So think of language model like this. So language model is nothing but distribute prediction. So let's suppose you have a language model over here. So in here you give it some context. Okay, so this is the context you give it. The context can be, the first thing is you have these words or whatever you have these sentences. So you convert them into tokens. So what you do is you first tokenize, so that when we follow the paper you understand it. So we tokenize the thing. So what's the meaning of tokenization? You basically have this text. Let's call this text. So you chunk this down. So you chunk it into smaller subwords. Even there is word level tokenization, subword level tokenization. So let's suppose I'll say this. Suppose hello Mahmood. It's like this. So it will chunk the words. And token, there are different types of token. This is a topic in itself, but here I'll just present the gist for the people who don't know it. So let's suppose if it's a word level tokenization, so it will make a token like this. So this Mahmood will be, this will be a token, this will be a token. So it will tokenize the whole thing like this. So these are called tokens. So now the thing is, this is just an X word prediction. You have a vocabulary size, because all of this dictionary words come in the vocabulary of this language model. So now you have this language model. If you give it something, so let's suppose you give it the cat, you gave something like this, the cat. These are the two words. So what it will do is it will sort of predict the next token. Okay, that's why it's called as next token prediction. Next token prediction. So what will you do is, so you have this the cat, and this will go to the language model. There are a lot of blocks in the language model which does it. There is the embedding layer, the first layer, then there is let's suppose encoder blocks, then we have multiple layers again, then we apply softmax and stuff like that. So all of this process basically does only one thing. The thing that it does is it will take the cat, and it will try to generate a probability distribution. Let's suppose vocabulary contains words like sat, there, hello. A lot of words will be there, okay, in the whole vocabulary size. So it will generate a distribution, okay, so it will generate a probability distribution. So by probability I mean, so it will say with 0.1 there is a probability, 0.1 probability that the cat will be followed by the word a. So there is a 0.2 probability that it will be followed by this. So there will be this probability will be over all these words, all these vocabulary size words. Then what do we do is we sample one word among them, okay, so we sample the words. So to just summarize, you have a language model and you give it some input which is called as context, and what context does is so basically we want to predict next words. So all of language models, there are different blocks in the language, they only do one thing, they come up with a distribution, they come up with this probability distribution. They said that there is this much probability that this context will be followed by this word. As in this case, the cat will be followed by with 0.1 probability, the cat will be followed by sat with 0.2 probability, and the distribution is there. And then you sample the words, and there are different methods of sampling as well, okay. You might have heard about beam search, greedy methods. A lot of methods are there where by the help of which you sort of get these you sample from this. Let's suppose we sampled the sat. Now the sentence becomes the cat sat. Again the same thing will happen. This will go into the language model, okay, it will again perform the same things that it performed earlier, and it will again come up with distribution, okay. Then we'll sample the next token. We'll keep on sampling token till the end of those tokens comes. That's how language, that's why this is called auto-regressive models. Why? Because you can see that from this we got this sat, then from this let's suppose we get something like this. We have a question. Yes, questions, go ahead.
Sir, is it like after training this happens to predict the next word?
If you see, this is one step. Let's suppose take inference and the train. So in training, what you basically, I'm just telling you the inference part. How do we inference it? So in the training, what you basically do is, I'll tell you, you have a sentence like this. You have the cat sat on the mat. You already know it, okay. So in the training, what we basically do is, so this, let's suppose, is a training example, okay. So this is not just one training example, this will be multiple training examples. Let me tell you how. Let's consider this x. This x means training data, y means target. So for this, the cat is target, okay. Cat sat on the mat, okay. So if you see, for this word, the cat is the target, for this cat sat is the target, for this sat on is the target, for this is the target accordingly. So let me tell you how. So first you will have this x will be the, so its target will be cat, then you will have the cat, its target will be sat, okay. Then you will have the cat sat on will be the target, okay. So you can see this is our x and this is our y. These are our predictions. So does it make sense? This is,
Yes,
this
sir.
is training. So this is training.
I got it. I'm telling, when we give a prompt to LLM,
Yes.
so वहाँ पे कैसे work कर रहा है?
हाँ,
Because
so
we
the
give a
same,
small prompt.
now you give a prompt, you gave the cat, okay. So what it does is you give it to the LLM. So what LLM does by all these blocks, there are multiple blocks of LLMs, okay. The main of them is a decoder block. So you have embedding layer, then you have these decoder blocks, and after that you have different softmax layers, you have these multi-layer perceptrons. So what they do is, they basically, all these things come up with a probability distribution. So you have vocabulary size. Now you have vocabulary. Vocabulary is list of all the possible words that are there, list of all the possible words. So what you do is you assign probabilities to them. You assign the probability because you have this. So with this you give it to language model. So you give this to the language model. Now language model assigns probability to these words because these words are already in your vocabulary. Think as a dictionary. You have a dictionary with you. Now what you have to do is you have to give a probability distribution to all these. What is the probability distribution? That basically means the thing should sum up to 1. So if you sum up all these numbers, the probability that you assign them, it should sum up to 1. So there are different words, as I wrote there, they, them, something like this. So it will give numbers to this. So after that we will sample 0.1, 0.2, 0.3, which I gave the example over here. the cat will go into the LLM. So the only LLM, what will it do is, it will somehow come up with the problem. It will come up with numbers. These numbers will be assigned to these different things, to these vocabularies basically, and then we'll sample them. Okay, once we sample it, let's suppose, after that what we do what's called as cross entropy loss. We'll see, okay, how much bad or how much good the guess was. Okay, how much problem, and then you try to reduce that cross, and you say, okay, I want to minimize this. I want to minimize this cross entropy loss, because let's suppose if I said the cat. So if I, let's suppose, sample their word, so there will be a huge penalty on me. So I'll say I got it very wrong. So next time when I have this example, I should maybe choose some other word. That's how the training happens. And the inference part, give it a context, predicts next token, then again comes back, okay, and goes to the context back, and then it keeps on going till it finds the end of sequence. Because we have special tokens, then we have special tokens called as start of sequence and end of sequence. So start of sequence tells the language model you are starting the chat now, you are starting the next word prediction, and the end of sequence says the generation is complete, you can generate this much only. Okay, because sometimes many of these after having a particular context, it stops at a particular thing, so you have to stop it, and it generates this end of sequencer. And sometimes you also restrict it by maximum length. You should not go beyond this length. That's called context length. You should not get, let's suppose, the maximum number of tokens you can generate is this much, because otherwise the more the context length, because the algorithm is order n square. So if you see attention, that is order n square. So let me not go into those details. Someday we'll take LLMs in detail, but I'm just giving a primer to this. Am I making sense?
Yes, sir. Yes.
Okay. So this is the language model that we are doing now. As you can see. So now let's go to the paper back, because I wanted to explain one term. So for that I had to. Now they say we introduced our first generation reasoning model, DeepSeek R1 0 and DeepSeek R1, and DeepSeek R1 right here. These are the two things that they actually did. So what usually they do is they'll give a whole lot of text in that's called as pre-training phase. Okay, because they have to train it. They train it with a large corpus, and that data is not high quality data. Okay, the training goes into multiple steps. You have whole the internet, you scrap it, and then you give it in different languages. So now you have trained it. Now somehow it has a world sense. Now your language model has learned something about the world. So now the next step that you do is you do supervised fine tuning. Okay, SFT they call it. So what is SFT? SFT basically is you have a very high quality data. Very high quality basically means you will have the question, its answer will be given to this. Okay, you have something like very high quality data, and you fine tune the model on that data now. Because initially you gave it a very low quality data that was scrapped from the internet, and that was from here there. And second step is that SFT. Now you have prepared yourself, that high quality data has been prepared actually, and because we want the model to behave in a certain way, so that we just fine tune it and we just give it this information that this is the sort of input we want. That because let's suppose in SFT we said be sympathetic to the humans, okay, agree to humans, do not try to disagree, do not try to do this. So some sort of data like that. Yes, questions, go ahead.
Sir, when you said that we give a large amount of unstructured data to the LLM in pre-training stage, what is the model expected to learn from this unsupervised data? Large amount of unsupervised data.
It's not unsupervised. It's again supervised and neither unstructured. So this data is not high quality. That's what I said. By high quality I mean ki it will have something, because if you see internet, so on internet there are a lot of mistakes written in there. Sometimes it's a good quality data if it's from books. So what is it expected to learn? Basically you have a sense of grammar, you have a sense of like these things, what things to attend to, because that's how humans learn. We learn a lot of mumbo jumbo. So usually what we try to do is you give it everything that is possible on the internet. So data is the thing which has all the assumptions that we assume about the world. That's what is engulfed in the data somehow. So when you give it in the pre-training phase, so you somehow expect that it will learn something about the world from this data. Let's suppose if you ask it some information about, let's suppose this word, as I gave the sentence, the cat sat. So usually it has seen a lot of sentences where the next word was on the mat, something like this. So it will somehow find those structures. Okay, it is trying to learn these patterns in the initial phase. But if you see it, it will because this data is sort of not very high quality, so sometimes it may deviate, it may give biased answers because the internet is biased itself. So you have to tune it after that. Yes, go ahead. Question.
Follow-up question, sir. You said that the data in the pre-training phase is supervised. I would like to ask what would be the labels to this, the data fed in pre-training stage?
Here, This is your X input, this is your target.
Oh,
That's what I spoke. X means input, Y means target. This is your input and target.
acha, so it is expected to learn the somehow the probabilities of what would the next word
What
given
would
the
be the
previous
next
sequence.
word? Yes, yes. So from this, actually, it gives a lot of power. So even if you think, how do we speak? Let's suppose if I say something, and you have interacted with me enough, so you will be able to guess the next word sometimes. Most of the time, let's suppose if I say, "Welcome to the," so what will be the next word?
Lecture.
Lecture, yes, session, class. So because you have now, and you know a little bit of context because you have spent some time with me. So if I say welcome to the, your brain somehow predicts that. So this next word prediction is a huge thing. Because it seems so simple, but it's a huge thing because this is how our brain operates. Because our brain operates on predictions. In the neuroscience lecture also, I think we discussed it because we have this frontal lobe. There is a theory called as triune theory by McLaren. So there is a top-down control and a bottom-up control. Why are humans so special? Because we have developed this frontal lobe so much, and that's the reason we also go in depression. Because sometimes what happens is you anticipate things. There is a beautiful quote by somebody which says, "You hurt yourself more in imagination." Okay, things are not worse actually, but you imagine the worse. Okay, that is because of this frontal lobe. We have this frontal lobe, then we have occipital lobe, parietal lobe, and this frontal lobe is responsible for planning, reasoning, and sort of thinking, okay, what will go after this, what can happen after this. Even in chess you will see the strategies, and usually what happens, all the human brains do it. Let's say when I speak with you, so your brain also adjusts, okay, I should not say this word, probably it might offend sir. I also say, okay, I should not say this, maybe they don't have enough knowledge, I'll have to deviate these things. A lot of things go, a lot of planning goes into my head before speaking also, similar with you. So that is the next word. And I was recently reading a book, so there it mentioned that the brain actually is a prediction machine. It's nothing but a prediction machine. It predicts some things. Okay, and what happens with the prediction, a lot of things that can happen. The biggest prediction gives us so much power. So you see, and that is the thing we wanted to replicate. But those predictions should be sensible predictions. You should not predict randomly. You should predict somewhat which is making sense. And that's why we came up with attention and stuff like that. Okay, and we will discuss it later. But I hope I sort of gave you some why this language, why they work, why should they work even.
Yes, yes, makes sense when I relate it to naive Bayes algorithm or Bayesian training. Yes, now it makes sense.
Yes, so now if you see this, you have this training phase, the pre-training phase where you pre-train these things, and the second thing which I said is was SFT, that is supervised fine tuning. So in this, what you basically do is you have very high quality data. Okay, you have prepared it, probably some people have spent maybe months. People in Nigeria usually do it, they spend months on this data, and the people from third world countries usually, so that data is given to them so that it makes sense. So that is what is called as supervised fine training. So why do we do that? Because we expect human like responses. Okay, so this is the thing, and we expect this word to follow next. So when you see the model, if it is, that was the assumption was if you fine tune it supervise, if you do SFT, so probably model will learn better because initially it has the world knowledge. Now it has to be somehow sensible to humans. It should speak like a good human. It should speak like a sensible human in a professional way. You have to give it the data like that so that you fine tune on that. Okay, but what this paper has done, if you see, they have removed this SFT stage. They have removed this supervised fine tuning. Yes, question.
सर जो हम प्री ट्रेनिंग में मॉडल एक्चुअली these learn the probabilities of
Yes, yes, yes.
predicting the next word.
Yes.
Is it like that?
Yes, yes, yes. They learn the probabilities. वो probability assign करते हैं. They assign the probability to all that vocabulary. जितना भी vocabulary है, जैसे मैंने लिखा, we had a, there, they, them. Let's suppose hi, cat. All these words will be there in the, not words. Actually, this is the vocabulary will consist of tokens. I'm just making the word level tokens. So these will be assigned probabilities. Okay, let's suppose you have only 1, 2, 3, 4, 5, 6, 7 words. Let's say this is 0.1 probability. This is, let's suppose, 0.2, 0.01. Okay, 0.001, something like this. Okay, let's say we have 0.06. Okay, something like this. All of this should add up to 1. Add up to 1. Okay, then what you basically do is if you take the highest probability word next, this is called sampling. So this is called greedy search. Okay, because now you are taking the highest word sampling word, so it will not be more creative. But usually what you do is you basically set the temperature after that. So in softmax, because you usually don't get these directly these probabilities, you actually get some scores, get some values. So in order to convert anything that that's a bunch of values, if you want to convert them into probability distribution, you apply softmax. Okay, so softmax converts those things into probability distribution. Now on that softmax term, you give one more term that's called temperature. Temperature basically says, okay, how much the creative model should be. You will go into all these equation detail. I am just throwing terms at you, but I hope that you are understand. So this greedy approach, if you use, so it will now sample this word because it has 0.2 probability, highest among the all. So let's suppose we had once upon a time. Once upon a time was the context. Okay, and then this was sampled. This there was sampled, and now this will go as a context. That's why context length matters. Okay, context, this is called context length. So how much maximum number of tokens can you feed? Okay, because after a while it can't proceed the context, it will have to leave after that. So if you see even the GPT doing that, so if you converse a lot with it, so it will miss what you said earlier, because it may be context, it goes out of its context length. Okay, now we have a lot of context, like we have 16 million tokens, even more than that. Even DeepSeek has a lot of I have not we can say exact numbers, so we'll see that. But the context this matters a lot, because the more context you give, the more time it takes for the computation. Okay, because the operation that you do is I think one of the operations that you do is attention. Attention, it's a quadratic operation. Like simple attention is a quadratic operation. So once you give this, yes.
Yes, this pre-train and this fine-tuning, these are two steps.
Yes.
Do we need to have the same language, then it will perform better, or like if we are,
you can give it anything. So what you basically do is on the internet, it is initially trained on every data. It is initially trained on whatever is on the internet, numbers, code, bulb molecules, English text, and all of this stuff. So that's why I said it's a mumbo jumbo of things. Okay, so it basically predicts things like that. Okay, so after that, what will happen, because usually the things are English, that's why these things perform good on English, because there's a lot of English text on the web. So in the second stage, that's where you come in. Okay, you give this maybe now these language models can understand multiple languages also, because in pre-training they have seen a lot of corpus. That's called usually a corpus, because they have seen a lot of this data about different languages. So it struggles in some language for which we have less. So Kashmiri, it can still maybe give some answers in Kashmiri, but it will mess up. Why? Because it has not seen enough data of Kashmiri. Okay, because once you seek some Kashmiri word, and then it will follow based on that, because in the books or whatever data it was trained on, Kashmiri words are followed by Kashmiri words usually. So if you give it a Kashmiri prompt, there is a high probability it will give you back Kashmiri, but the Kashmiri won't be good. Why? Because there is very less data on which it was trained. But English, you have humongous amount of data. That's why if you give it prompt, so it doesn't make grammatical mistakes in English, because there are huge amount of books, and even it does not make on famous languages also. Even it can speak English on which we type keyboards. Let's suppose if I have to write a message in Hindi, because I resort to English, so we usually English, and there is a lot of data that is generated. So it's also trained on that. Okay, whatever you give it, it will predict next. That's why I said tokenization is very important. You don't tokenize it word wise. Okay, you tokenize it token wise. So token is a basic unit basically. So it can be even one character, two characters. There is something called as BPE also. So a lot of these things are there. So token is not necessary that we can have a word of token, because usually we'll say that, okay, once space comes, then we'll consider it a word. Some language don't have a sense of space. Okay, this tokenization is different for different languages also. So and some for this even Facebook has this BPs. They came up with the Facebook came up with this. There are different types of tokenization. But what I am saying is, it is fed the whole data. Okay, and it is broke down into tokens. And even these tokens, you don't see these words. So what you basically do, you abstract all the details. So you have this vocabulary. So you convert it. You encode this. You say that now let's suppose I have unique all the data that I have. In that, once I tokenize it, let's suppose you had some 50,000 plus tokens, unique tokens. Okay, you assign them numbers. Okay, you have to encode them, because you won't work with them. So you have a vocabulary size. It will be a mix of English, Hindi, Urdu, whatever it is. The vocabulary size will consist of tokens, and tokens will be a mix of languages. And even it can be symbols also. It can be, let's suppose, some Mandarin, some other things, whatever you like, whatever was in the data. Because when you tokenize the data, so you got a bunch of building blocks. That's why I'm saying 50,000 plus tokens. I think Llama is using 50,000 plus tokens. You see, in English alphabet, if you see even at, let's suppose, word level, there won't be let's say 50,000 plus words. I think it's very difficult to come up with these. But when you break them in tokens, so you have a lot of these things. So, and this vocabulary size is not just restricted to English. It can be anything. Does it make sense?
Yes, sir.
Okay, so I was here. So what I said is pre-training stage, and then you have this SFT. Pre-training is to understand the world from the data, and SFT is to let it behave actually like a human. If you want to make it a chatbot, so it should have certain properties. So you give it that by SFT, and then you also hardcode some rules. So you make that is a different thing we use. I will not go to that. So again, coming back to the paper. So if you see what they have done here is, so DeepSeek R1 a model trained on reinforcement learning without SFT. So they have not used SFT. They have not used this second stage as a preliminary step, and demonstrates remarkable reasoning capabilities. Through RL, DeepSeek R0 naturally emerges. You see this. This is the question to Fahad's. This is the answer to Fahad's question. Once he said we understand it. You see, DeepSeek R1 0, they didn't understand it. It emerges naturally. So if you write something in a scientific paper naturally, that means you don't understand. Okay, we don't understand these phenomena. So you see, DeepSeek RL 0 emerges with numerous powerful and intriguing reasoning behavior. Intriguing means we don't understand why it reasons in a certain way. However, it encounters challenges such as poor readability and language mixing. So they have also given this problem. So what I will do is, so now if I'll go back to Notion. Now I'll add an abstract over here. So whatever things I understood so far, I'll write them. So this is, I'll keep an h2 tag. So abstract. So I'll write high level points. So I'll write this numbered list. So the first thing that I'll write is no SFT used. Okay. Rather than this, rather RL is used. And then second thing, what I could remember from this is some intriguing, some intriguing reasoning behaviors emerge naturally. So these are the two important things. So what I usually do then is, because I usually write in the rough, so I'll just improve the writing. So here we have an option of improve the writing. So it will improve the writing. I'll accept it. So you can see the model uses reinforcement instead of supervise this. Intriguing reasoning behaviors emerge naturally from this approach. Okay, now going back here. And after that, you can see how it encounters different challenges also. So the challenge that it has, poor readability, and it mix of language, because when you give it something, so because of this RL approach, what it does is, so it will sometimes it will not read as expected. Okay, and it mixes of language. It was mixing Chinese and something. It was giving answers in multiple languages. So okay, that's what I said. That's why SFT is used, because it gives multiple. You ask it something, because in the vocabulary size itself, so there is a lot of tokens are there. A lot of tokens of different languages are there. So it will mix up them. Okay, so because it was not supervised fine tuned. So it was just RL was given, so that's what they said. However, it encode challenge like such as poor readability and language mixing. So language mixing, you got it now. Why language mixing? Because it was not fine tuned by supervision, and high quality data was not given to it. So it still is living in that world. Let's suppose me, I sometimes juggle of languages. I sometimes use Hindi, English, a mixture of that. So because it has seen a lot of languages now, so it will mix up these languages. And many people, when I was discussing with them, so they commented that it is mixing Chinese and stuff. Yes, go ahead.
सर एक्चुअली मैंने आज ये डीप सीक यूज किया था, तो मैंने उसमें दिया था ये कैन यू लिस्ट द स्टेट्स ऑफ इंडिया, तो उसने कुछ एरर दिया वहां से, तो फिर मैं कुछ वही देख रहा था कि व्हाई इट्स गिविंग एरर। फिर मुझे पता चला कि जो अरुणाचल प्रदेश है तो उसका कुछ कॉन्फ्लिक्ट है, so that's why it's not giving full state, so it's showing error.
One error again today, one error could be क्योंकि बहुत server load है उस पे. There is a lot of people who are using it, because I also tried in the morning. It was showing server is busy, this and that.
No,
And
sir, it was giving my answers to other questions, but
okay, okay,
probably
okay.
this question it was not giving. So फिर मैंने वही किया, थोड़ा किया कि क्यों नहीं हो रहा है इसमें. फिर there was some answers. It is still controlling by these Chinese government. So does it like कि अगर इसमें fine tuning है ही नहीं, तो why it is giving an error?
It is reasoning. It is reasoning on its own. So I don't know about the policy Chinese might have restricted, but they haven't. As far as I have seen it, they haven't restricted the things. So whatever
Yes,
you give it, it was given.
महमूद ने अभी टाइप किया है वो एरर.
Let me just
when we
see.
get this.
So he's saying, Lisa State, sorry, I'm not sure how to approach this type of question. Let's chat about math coding. Yes, so even they might have, as I said, rules might have been imposed, because sometimes if you ask a controversial question, it will try not to answer. It will say ki, no, I will not try to answer, and maybe that is because it was rules were imposed on this. You should not do this. You should not. That's what I said. After supervised fine tuning, you also impose rules. But here they are not mentioned in the paper, so I'll stick to the paper. Whatever they are saying in the paper, I'll stick to that. So because I cannot defend them, and I should not defend actually. So the challenge is that the first thing is there is poor readability. Okay, and poor readability is there, and after that, the second challenge, it mixes languages, mixing of languages. Okay, and then we can find the rationale. So here I can usually what I do is I'll add question mark, yeah, or I will add some comment. So what I do is I usually add this. So I'll maybe want to find that tag. So I'll add is why is it so? Okay, I'll try to find it because it's an interesting question if we could answer it. Okay, now coming back. So then to address these issues and further enhance reasoning, we introduced DeepSeek R1. Okay, they were speaking about these two things, DeepSeek R1 0 and DeepSeek R1. Okay, so this is what they were speaking about. So they have said in order to sort of navigate these challenges, so they have used this, which incorporates multi-stage training process and cold start data before RL. DeepSeek R1 achieves performance, and then it gives the comparison performance chart of this, and this is the gist of the paper. So basically they have achieved the high performance. So this is why they have put it, because it was winning on every benchmark almost. Then this OpenAI's that O1. So that's why this benchmark attracted people quite a lot. Okay, so this is actually worth taking from here. So I'll usually take a screenshot from here because I don't want to write text, and then I'll paste it onto this. Okay, so I'll write at the heading comparison, result comparison. So now I sort of understood what is there in the paper. Okay, now I'll go roughly through the outline once. They are introducing, there is an introduction which probably will say something about language models, and then they'll say what cold start means and how do they use this cold start, and then they are giving the overview of the paper, then training template. They might be showing examples in this, and then they are also discussing something, and then they are summarizing some results, model, and conclusion. What is their model doing? So I think most important part would be this training, but still we'll go through it. Go through the introduction again. So if I go through the introduction, I'll just skim through it. So if I go through the introduction, so in recent years this has rapid iteration, so everybody knows this now. You know a lot about this. So now basically it is claiming that progressively diminishing gap towards AGI, which I completely disagree. Recently post training has emerged as an important component, because you had pre-training or training, and then you had this SFT component full training. It has been shown to enhance accuracy on reasoning to align with social values. That's what I said. Social values, basically how should you behave and adapt to the user preferences. That's what I said. You have to behave as professionals. You should not curse them, all while requiring relatively minimal complex resources, because now initially it would use a lot of resources. Why? Because you are feeding a lot of data to it, and the second phase it usually uses relatively less data in those post training stages, in which one of them is SFT. All the while requiring minimal of this. In context to the reasoning capabilities, OpenAI has released the series of models were introduced inference time scaling by increasing the length of the chain of thought. So what chain of thought basically is, this is a topic again in itself, but I'll just tell you what chain of thoughts is. So let's suppose if I ask you some question, so based on that you will give me an answer, but can you reason for first? I'll tell you, okay, what made you arrive at this result? What made you arrive? So if you have not memorized it, if you have not mugged up this result directly, so if you just go with the first principles, what is the thought process that goes into your head? Okay, so let's suppose I'll tell you, can you prove x plus y raised power n? Like, can you prove the binomial theorem? So you'll reason. If you don't know the answer directly, if you don't know the proof directly, you'll reason from first principles. Okay, what can I do? The first thought that comes to my mind, I should expand it. Okay, let me do that in front of, because that was the topic I was going to discuss maybe today in permutations, combinations. So I'll show you it here. So what I said is, if I gave you a question to answer, I said, okay, this is x plus y, it's the whole square. You know, this is x square plus y square plus 2xy, something like this. Because when you generalize the result, you get a binomial theorem. Say x plus y raised power n is equal summation of nck. Okay, k goes from 0 to n, x to the power let's suppose k, y to the power n minus k. So this is the binomial theorem. This is the result of the binomial theorem that you have to prove. So let's suppose if I don't know the answer, so how will I approach it? Like from first principles, the first thought comes to my mind, okay, can I expand this? Okay, this is a thought that came to my mind. Okay, I should expand it. Okay, now I'll do the expansion. I'll say x plus y, x plus y, x plus y, and so on till n times. Okay, n times. Okay, now the thing is, what's the second thought that comes to my mind? Because these are multiplication, so that means I have to take each one term from this. Okay, so this is the second thought. So this was my first thought. Second thought came when I expand it. Now I have to multiply them. So multiplication will result in taking one term from each unit. So here, if you see, I call this a unit. This is my unit, because if I have to multiply, I'll maybe, let's suppose, take x from here, I'll take y from here, take x from here, take y from here. So I'll have to take one units from here. So that is my reasoning process. Expand and multiply. Okay, so what does this give me? So this information will lead to something else. Let's suppose, what will it lead me towards? So I'll say, now the basic thing is, I'll get x, the combination of x, y. I'll get, let's suppose, x raised to power something, x raised to power k, and y raised to power n minus k. Why so? Why am I saying so? I'll get these. The rationale behind them is because I'll take each the term. I'll basically get n terms. I'll get, each term will consist of let's suppose n values. It'll have x, then y, then x, something like this. So there will be n of n such terms, because I have these n units. So from them I'm taking one term at a time. So that tells me, let's suppose I'll have k of x and y of n minus k, because the total sum should be n should be equal to k plus n minus k. So this is equal to n. That's why I said k and n minus k. These are the number of terms. Now the question is, how many of such terms will I have? Okay, how many of such terms? So from the permutation combinations, I know I'll have nck number of such terms, and then I'll have to sum them up, because this k will start from 0 to 1. This is the chain of thought. So how many of you understood the process? How many of you understood the process? Nobody? I can't see your hands. So basically what I went through is, I actually went through a process. I started to reason from first principles. Okay, what might happen? Okay, this thing came to my mind. Sometimes I trace back. No, this is not good. So what you do, if you see DeepSeek R1, so if you click on that reasoning R1, so it will reason. Okay, let's go through that also. DeepSeek, I think this is the chat. Okay, here you can click on this DeepSeek R1. So I'll say prove the binomial theorem.
The screen is not visible.
Oh, sorry, just give me some time. Here if you see it, so I'm asking it prove the binomial theorem, but I'll give it specifically using combinatoric, something like this. Okay, it will figure out the spellings on its own. Now it is thinking, you see, okay, so I need to prove this thing. The first thing is, oh, let me remember what is the binomial theorem. So it states for this real number, so it is first remembering what binomial theorem is. Okay, now the question is, to prove it using combinatorial proof often involves counting. Okay, so it got, oh, I have to use this proof, so it means I have to count things. So maybe I need to think about expanding x plus y, and that's the first thing that came to my mind also. So if you see, so here the reasoning of me and this DeepSeek is similar. So I said, okay, maybe I need to think on how expanding this relatives combinations. Let me start by recalling how expansion works. So first, because it again thinks deeply, okay, how can I expand this? So it said you essentially multiply n of these terms. Okay, each term in the expansion comes from choosing either x or y. The same thing which I just said. Okay, so you will take either x or y from each of these units and multiply them. So for example, if you choose x from each of the n, you will get x to the power n if you choose n of these. So if you choose y, one binomial, and then you will get x n minus 1 and rest and just one y. So it is giving the same. Oh, wait, then it says therefore the expansion term will something like this, which I came to. Wait, that seems almost like a proof. Maybe I need to formalize it more. Okay, now I'll formalize it more. After all of this thinking, so it is still thinking. Okay, it is trying with the examples as well. Okay, let me expand key, whatever I proved, was it correct or not? So therefore common proof seems valid. But here it got it wrong. Why? Because it is trying to check the proof, it's trying to see the things manually. This is why it can fail. The problem is because proof by example is not a proof. Okay, so it actually came up with the right this thing, but it was trying to check am I right or not. So it sort of used the human example. Okay, I'll use example. But you know that proof by example is not a proof. So it just used two examples. It said x plus y whole square comes out to this. So according to the binomial theorem, this should be this. So which matches. So one example. And then it did example, another example. N is equal to 3. So it equal binomial this. So let's see choosing y and this. So it says which matches. Similarly for this. So it is now generalizing. So this is called strawman argument. So here I will disagree with the thought process. Here. And then it is doing some final check. Is there any perspective of potential mistake in the reasoning? Let me think. Sometimes common proofs can be accused of being just intuitive, but in this case, the counting argument is precise. Each term coefficient exact, and this is a good argument for here. Yes, I think it works. The binomial theory is fundamentally about counting, so let's go. Final answer. From each term, count the number of terms, summing all the possible overviews. So this is the chain of thoughts. So it has a thought, it follows that, there's a chain of thoughts after that follow. So if there is one thing that's wrong, so whole of this chain of, that's why this chain of thought has a problem as well. So how many of you understood this? How many of you are understanding it? So this thing has a problem as well. Why? Because if you got a single point wrong, let's say you got a single point wrong. So what you'll do is you will keep on saying, oh, probably this is the good reasoning point, and you will just deviate from the reasoning. You are now reasoning differently. So there is a good quote which somebody said, initially these language models were hallucinating, now they are gaslighting. So what is gaslighting? They try to convince, because now they think chain of thought is what works. So they will be convinced, no, this works, and they'll give you rational also. They'll give you rational, no, I thought is, and they'll give peculiar examples. That's why I am right, I am wrong. Why? Because now the point is it thought in a certain way, and it is now sort of preserving that thought process. It's saying, no, I am right in that thought process, and it will find weird corner cases, even if it is directly wrong. So okay, remember this quote, earlier they were hallucinating, now these reasoning models are gaslighting. They are trying to convince you. Going back. Okay, and then whoever has the chain of thought. So this approach has achieved significant improvements in various reasoning tasks such as mathematics, coding, scientific reasoning. However, the challenge of effective test time scaling remains an open question for the research communities. Several prior works have explored various approaches, including process-based reward models, and we can discuss about them. I'm just going through them. Reinforcement learning and search algorithms like Monte Carlo, the tree search and beam search methods. However, none of these models can achieve a greater reasoning performance comparable to OpenAI. So what they did is, they said there are a lot of methods that can be explored in order to get this reasoning right, but nobody comes close to OpenAI. The name is OpenAI, but what they are doing is nobody knows. Okay, even somebody actually there was a guy in OpenAI. He was asked, okay, what are you doing in OpenAI? He said, wait until Chinese replicate it. He said it, I think, before DeepSeek R1 came. I knew about this statement at least 10-15 days ago. I was reading some article blog, so there he said, somebody asked him a question, when will you release this, or what are you doing in this O1 model? He said, you just have to wait till the Chinese replicate it. So now what they said is, he said that the paper is saying that there are different methods, but nobody comes closer to OpenAI's series model. Okay, questions, I'll go to next paragraph after that. Yes, go ahead.
My question was, sir, what is reinforcement learning? Can you please explain it in short? And how they have
Yes.
achieved.
I'll tell you. Let me go through it. If it comes more often, I'll tell you what they have done. So they have used reinforcement learning. So let me just brief you about reinforcement learning before I go ahead. Okay, so what reinforcement learning basically is, you have environment and the agent. So you have an agent and environment. So after this agent, I won't go into mathematical details. There is something called as MDP, Markov decision process, which I won't touch. So I'll just give you into the explanations of what is this reinforcement learning. There is something called as reinforce and reinforce also. Okay, you might have not heard about reinforcement learning. So what happens here? So you have an environment. So you have an agent. Agent has these states. Agent is in some states. Okay, agent can take actions. Okay, based on these actions, it will land into some other states. Okay, so it will land into some other states. Let me give an example like this, which I think Omar Jamil was discussing in his Discord session. It's a good example. It makes the point through. Let's suppose you have a cat over here. Okay, you have the cat's food over here. But usually cats, they hate water. Okay, and they hate, let's suppose, this broom. Okay, broom by the help of which you clean the stuff. So now the goal of the cat is given the goal that you have to eat the food. Now cat has to find an optimal strategy somehow, because cat can only move either up or left. Let's suppose cat is restricted. You can move either down, or let's suppose left or up or right, something like this. You cannot jump through the diagonals. Okay, now it has to find a strategy. What should I do? Okay, so that strategy, sometimes if it, let's suppose in this position, if it goes to left, okay, there will be a penalty associated to it. So it will get, let's suppose, some -1 penalty. If it is, let's suppose, somewhat here, cat is here, and if cat goes downwards, it goes to the water. So here penalty will be, let's suppose, -10. It's a huge penalty. Okay, and if cat somehow comes here and goes down, so let's suppose penalty is +100. This reward is +100. So you basically have a reward and penalty based on the actions you take. You are in a particular state, and once you take an action basically, these are defined. These are a set of things that you can do, and you can land at different states. So once you take one action, based on that you land at another state. So you will have some reward or penalty based on the action you took. Okay, so this, now we have a problem. The problem is called as exploration versus exploitation. What is this problem? So now you have to explore different strategies, but sometimes you know that I have some strategies by the help of which I get good rewards. Okay, you have to exploit these things, whatever you know from the actions. Okay, if I'm in this state, if I take this action, so based on this I get higher rewards. So now you have explored them. So you can exploit the explored states wherever you see higher rewards. So you can keep on exploiting, but there is a downside to that. Maybe you haven't explored enough. You could have got more rewards. So you'll have to balance this. You'll have to still explore and exploit whatever you can. Or they have to find a fine balance between exploration and exploitation. So this agent interacts with the environment, and it gets either reward or it basically comes up with a policy. That's called usually policy, and that policy is denoted by this pi. It comes with this policy. Okay, it tries to find an optimal policy where it gets good reward. Okay, that's how humans work also. If you see in the one of the neuroscience lectures, we only had one. So if you hear that, I asked a specific question about reward system. How is our reward system wired? So I was speaking about this. So what the things I assign more reward to? Okay, it depends on, because all the humans are different and we have different reward systems. Okay, the reward is basically dopamine rush. So how much dopamine is now released based on activities. So that is different for different humans. So this is RL system. Does it make sense? Yes, question, go ahead.
Sir, how does this reinforcement learning framework, this agent, state, environment, and everything, reward penalty, how does it work with LLMs? Like
I'll
they are
tell you how. So how it does is, so what you basically do is, you let's suppose have this, the cat sat. Now what it does is, it will predict these, it will have certain predictions. Okay, so it will have, let's suppose, mad, this and that. So for all of these, a reward will be associated. Okay, so if you do this more, so a reward will be associated. So if you sort of came up with this, a reward will be, let's suppose you are doing some mathematical proof. So if you follow this token with this, so a reward will be associated with this. So you associate reward if you get it more accurate, because you have this high quality data with you, or you, let's suppose, now have the data, at least you have the full proof with you. Okay, you have full proof of something. So what you give it, you now give it and you say we expect this after that. So if it keeps on doing that, if you give it, let's suppose, mathematically, if you give it a lot of data, so it will try to find somehow the things that will give it maximized reward, because it has to land up to the right solution, or it has to land up to the right things. So it will somehow find that policy. Okay, what should I do so that I sample the right words? Okay, what should I do so that I give the enough the distribution should be focused on the right words? Okay, that's how you sort of use reinforcement learning in this. Okay, there is a lot of things going on. There is something called as DPO. They have used something called as GRPO. That they have used this. We won't go into details of that, but there are mechanisms of doing this also. So I hope at least you got the gist. How is it doing? So, and then you still don't know. So there is something called, we'll go through the paper also and we'll come to these terms. So right now, just hold your horses. Once we go to that, I'll explain you maybe few of these terms. So coming back here to the paper. Oops. So now we'll go through this. In the paper, we have taken first towards improving this language capability using pure reinforcement learning. This is the pure reinforcement learning I was speaking about. Our goal is to explore potential of LLMs to develop reasoning capabilities without supervised data. You should not give data. Without that, you should just give it in the pre-training phase. You should ask it, okay, reason now. Focusing on their self-evolution through the pure RL process. So they should evolve on their own through RL, through this RL process, which I said. It will take an action. It will be either penalized or given some reward. Especially we use DeepSeek V3 base as the base model and employ this GRPO, which I just said. Okay, so this is the reinforcement learning policy they said, because before you have to understand DPO before this, which I won't go. And as RL framework to improve model performance in reasoning. During training, DeepSeek R1 naturally emerged numerous powerful and interesting reasoning behavior. So it naturally emerged. You don't know why it did it. Okay, if you see, there is a good documentary of AlphaGo. Okay, AlphaGo is a game which is usually played by in many countries, and it's a very famous and very tough game than chess. There are worldwide competitions on this AlphaGo. So when this DeepMind came up with this AlphaGo's first, and it was based on the reinforcement learning. Okay, and it actually made some move which everybody thought is a stupid move. Okay, because it was playing with the best player of the world. Okay, initially in the 5 games. He lost, and he knew why I lost, because he made some stupid moves. But in one game, what he did is this AlphaGo made a stupid move. Everybody thought this is a stupid move, but that later on turned out to be a very, very good move, because now it has a lot of knowledge and it has a lot of things, because it has learned a thing. It's like this. So if I play chess, let's suppose, if I play chess with humans, so I'll learn strategies, but I'll be limiting the capability because I learn it from humans. Okay, chess is a world, it has simple rules. Now if you, let's suppose, let 2 players play the chess, like computer players which play chess with each other. Okay, they'll keep on going better and better, because both of these people, both of the computers want to win. Okay, so how will they win? So they will keep on trying out different strategies, trying out the best moves, because there are limited moves and it is not uncountably infinite. AlphaGo is more complex than that. So here that's what they said. This DeepSeek R1 naturally emerged with numerous powerful interesting behaviors. We can't explain why I did it, but it did it. Okay, you can't explain it why. Okay, so if you could have explained it, maybe you could have hard coded it. So after thousands of RL steps, DeepSeek R1 0 exhibits super performance on reasoning benchmarks. For instance, pass either one score on this increases from this to this. With the majority voting, the score further improves with this, matching the performance of OpenAI this. So it has these reasoning behaviors. So it is showing some data set on which it performs good, shows good performance improvement. So however, DeepSeek R1 0 encounters challenges such as poor readability and language mixing. To address these issues, further enhance reasoning more, we introduce DeepSeek R1 which requires small data amount of cold start data so that it doesn't do it, and multi-stage training pipeline. Specifically, we begin by collecting thousands of cold start data to fine-tune the DeepSeek this. Following this, we perform reasoning-oriented RL like DeepSeek R1 0. Upon nearing convergence in RL process, we create a new supervised fine-tuning data through rejection sampling. So the rejection sampling, basically, if you sample it, you reject one thing. Okay, so one thing is like, suppose you can select. Even GPTs are doing that. So it generates 2 responses. It says which one you prefer more. Okay, if you click on I prefer on this more, that's called human feedback reinforcement learning system. So what you do is RHLF, human feedback reinforcement, something like that. Okay, Can you see it? Why I'm writing it on screen? Can you see it? You can't probably. So human reinforcement learning through the human feedback. So where is it? So that's why when you let me just maybe take this. So if you see, let's suppose you prompted something to GPT. Okay, it will give you a response 1, response 2. What will happen? So it will then ask which response do you prefer. Okay, you will click on, let's suppose this, you will click on one response among this. So this is called as reinforcement learning through human feedback. Okay, human gave a feedback and then you had this RL technique. Okay, now this response, if you generated first, so it will be rewarded more, and they collected this data. Okay, what this is like sort of selection sampling. So you select one thing. So rejection basically means, so you keep on rejecting. If you generate, no, it is not good, no, this is not good, something like that. Let us go back. No, I think I can also see right on this. Good. So we created, and they created this new SFT. Now because they have this SFT through the rejection sampling on the RL checkpoint combined with this supervised data from DeepSeek V3 domain, such as writing, factual, Q&A, self-cognition, and retain the DeepSeek V3 model. After fine-tuning with new data, and the checkpoint undergo an additional RL process. Okay, taking into the prompt from the scenarios, all scenarios. After steps, we obtained a checkpoint referred to as DeepSeek R1. So they still are training. Okay, they are have one checkpoint which achieves performance on par. So what I understood from this is, this was very important. So from here to here, it was very important. Specifically, if you see this from here, basically we begin by collecting thousands of cold start data to fine tune the DeepSeek R. The problem, because it says the problem was this, and this is how they managed to resolve the problem. Okay, so this paragraph says how did they manage to overcome the problem which they earlier had. So you can just copy this, go back to Notion, and this is the answer of this. Why is it so? But at least the solution to this, how it got solved. Okay, so this is again assumption. This is not actually, maybe it might not be happening, something else might be happening. See my thinking process. So my process goes, okay, they are giving this explanation, maybe because of this it doesn't have this problem, maybe something else happened which you don't know. Okay, but still I'll write what the paper quoted. Okay, how a DeepSeek RL0 converts this, I'll maybe improve writing so that it comes in the same paragraph. Now you see how this challenge with poor readability and language mixing. To address these issues, we introduced DeepSeek R1 with a small amount of cold data. So here you can bold this up, and then we had this multi-stage training pipeline, because they are doing RL 2 times. We begin by collecting thousands of cold start examples. This is the first step. So in here, if you see, this is the first step in the data. So usually at this point, I'll make diagrams or something. So thousands of cold start examples to fine tune the DeepSeek R1 model. This is the second step. We then perform a reasoning oriented this similar to DeepSeek R1 0. Okay, so this is the second step. So these are the steps in the pipeline. Okay, and as the RL process near converges, we generate a new data through rejection sampling. So this is another step. Combining it with SF this and writing factual. So I think this whole will go, and data will this writing factual, and this. So this is the answer. We use this to retrain DeepSeek base model after finding the checkpoint undergoes RL process. We use this to and this. They use whole of this data to train this DeepSeek base model. After fine tuning, the checkpoint undergoes RL process kind of prompt scenarios. This final model DeepSeek achieves performance comparable to this. Okay, this is the process, the high level 4-step process, maybe 5-step process. Okay, that they were speaking about. So initially what they do is they collect thousands of cold start examples to fine tune this, and then after that they do the RL step, and as RL step comes to near the convergence, they generate this SFT by using the rejection sampling, and then they combine it with the supervised data they already had from this model DeepSeek V3. They already had this is a 600 billion parameter model. So and at the end we use this data and retrain this DeepSeek R1, and at the end again after fine tuning they use one more RL step. Okay, this is the stepwise process that you can see over here. I'll consider, and this is the final model. So this will Now this is the step, this is the pipeline. So this can be also converted to diagram. So what I usually do at this step, again, improve writing. Oops, so I did not select all the things. Make it point, paste. So now it gives this. Okay, these 5 steps which I extracted. Except the cold start, collectors 1000 data, initial RL, perform this, data generation by using this, retraining this, final step is RL. Okay, and you can after this maybe take screenshot and I'll send it to you also. I'll send it to you people. So how many of you are finding my process interesting of reading papers? Are you finding it interesting? So this is how you can maybe collect. That's why I sometimes Notion is called second brain, because you can have so much dumped down. And let's suppose if I revisit this paper after say 10, 20, 30, 40 days, or even let's suppose a year or so, so I still will remember this. I am keeping enough cues there, because this is where where they explain the pipeline. So we further explore distillation. Now they use distillation because they have to quantize these models. They have to come up with lesser. That's what distillation is. To smaller dense models using this QN, and they have 32 billion model as the base model. Direct distillation from DeepSeek R outperforms applying on RL on it. This demonstrates the reasoning pattern discovered by larger base models, improves reasoning capability. We open source distills QN and llama based models, and notably our distill 14 billion model outperforms the art open source this preview by large margins, and distill 32 and 70 billion set new record on the reasoning benchmarks among the dense models. So here I like to point one thing towards you. Now you see, you have to give a lot of data, and after that you have to distill it, and still the distillation model performs good. Now you see the problem in there. So that means there is a way that we can get these models, we can get these smaller models which performs actually good, but we are very poor on optimization. So let me make a diagram to explain this. Okay, this is usually the problem. So you had a huge data. Let's suppose you had huge of this data. You had a lot of data like this. Okay, you trained a machine learning model, and then you got a good model. Let's suppose. So you got a good, let's call it good ML model, good ML. But this model is too big. Yeah, right. This is too big of a model. Now what they do is they use distillation. Okay, they'll make the model a bit smaller. Okay, this is also a little bit good, but not as good as the earlier model. The thing is, we had to resort to this. We went to this first and to this then. Could we have done something like this? So directly from, let's suppose, data, and we could have had a smaller model. So this is my smaller model, and we could directly come up with this. Okay, this here we need to learn about a lot of optimization. Okay, this is not possible as of now because we don't understand optimizations quite well. Okay, state of the art is not like, because we usually take this day route. We go here and then make these big models which learn good, and then distill from these the smaller models. So if we could somehow find a way which will directly come to these smaller models without these additional steps. Okay, let's suppose we come up with this 7 billion or 32 billion or 70 billion parameter models which perform almost equally good to the bigger model. Okay, you just distill some stuff, and you can see that 600 billion parameters and 70 billion parameters. So there will be very marginal difference among the performances. So we still are exploring this path. Okay, as still science is growing, and we still are trying to find, okay, can we directly go there? Okay, just a comment over here. So now we further explore distillation from this. So I think we went through this, and then this is the contribution they have made. Post training, large reinforcement training. From this, now you have a solid background, even by reading just abstract and the introduction. By now you should have a solid background what they did. The only thing now you should be worried about is basically how they explain the pipeline, what have they done. Still we'll read the contributions. Post training, large scale reinforcement on this. We have directly applied this to base model without relying on supervised this and preliminary step. Because now you will see repetitions, a lot of repetitions. This approach allows to explore chain of thoughts for solving complex problems, result in development of this capabilities at this, making significant milestone for research community, notably the first open source. Let's skip it. We almost understood all of this. We understood our pipeline, DeepSeek R1. The pipeline incorporates 2 RL aimed states that we saw at discovering improved reasoning patterns and aligning with the human preferences as 2 SFT states that serve as a seed of the model reasoning and non-reasoning capabilities. We believe this pipeline will benefit industry by creating the better models. So This is the thing that you should look into. This pipeline is going to be very important. The pipeline we just decoded from the paper. Distillation. Smaller models can be powerful to demonstrate the reasoning patterns. The larger model can be distilled into smaller models, resulting in better performance compared to the reasoning discovered through RL. The open source DeepSeek R1 as well as API will benefit the research community to distill better smaller models using reasoning data generated by DeepSeek R1. We fine-tuned, so they have some reasoning data as well. So the data that they have collected. We fine-tuned several dense models that are widely used in the research community. The evaluation results demonstrate that distilled smaller models perform exceptionally well on benchmarks. DeepSeek R1 this 7 billion achieves this much, surpassing this. Additionally, DeepSeek this has this score, which on the live these results significantly outperform the previous models, and that's basically saying the same things. And summary of the result evaluation. DeepSeek R1 again describe the results. Knowledge on the benchmark like MMLU, this Pro, GPQ Diamond are on outstanding results, while its performance is slightly below than this on these benchmarks. So with scores of this, so while performance is slightly below, DeepSeek R1 surpasses other closed source model, demonstrates competitive edge in educational tasks. On the factual benchmark, simple Q&A, this performs capability, and this at small trend is this others. DeepSeek also exhibits. So this is basically what they have achieved. Summary of the evaluation results. Now the main part is here, the approach they have used. You get the training template. I'll still go through it. So previous work was heavily reliant on large amounts of data, supervised data to enhance model. You can see repeating sentences in paper. That's why you should learn to go through, skim through it. In this study, we demonstrate the reasoning capability. Okay, further improve can be enhanced. How many of you feel there is a lot of repetition in this paper? How many of you feel this? There's a lot of repetition. Okay, so this actually happens in almost with all the papers. If you read the way I showed you to read, you will feel there's a repetition in papers. Okay, so you will feel at least only maybe 2-3 pages are important, not more than that in the papers. Usually the rest of the things are either repeated or maybe it has been discussed somewhere else. So hardly you have to. That's why I say introduction, abstract is very important to read, so that you get the gist of what are they doing. As I said in the books also. So in the books you should read the content page and maybe the preface also, and the overview, how the book is basically assembled together. So all these papers are like that. We can take some other papers. I'll show you repetitions there also. And DeepSeek, which applies this checkpoint, thousands of this distillation. So there are 3 steps which are important. So first is DeepSeek R0, which applies RL directly to the base model, and DeepSeek R1, which applies RL starting from the checkpoint, fine tuned with thousands of chain of thought examples. 3, distill the reasoning model. So this is the overview. DeepSeek R1 0 reinforcement based model. Reinforcement has demonstrated significant effectiveness. So we discussed it as in our previous work. However, these works heavily depend on supervised data, okay, which are time intensive together, okay, because you have to give it and you have to say, okay, they assign this reward. In this section, we explore the potential of LLMs developing reasoning capability without any supervised data, focusing on self-evolution. Okay, you give it just the proof and ask it to assign the reward even itself. This will be pure reinforcement. We start with a brief overview of our reinforcement learning algorithm, followed by the presentation of some exciting results, and hope this provides. I think only part which is important is this. So what they do is, so in order to save training cost of RL, we adopt group relatively policy optimized GPRO. Okay, this was introduced in some other paper, which foregoes the critic model that typically at the same side the policy model estimates the baseline of the group. Specifically for each of this Q, GPRO samples a group of outputs. Okay, it group out samples this output. For answer of Fahad is coming. So if you have a question Q, okay, for each question Q, you ask it something. So what it does is it will sample a group of outputs, which I just said, and from the old policy, this because earlier there is a policy which is thought it is optimal. So from that old policy, it will come up with this grouped out. That's why it's known as group relative, and then policy optimal, because you are optimizing the policy. From the old policy pi theta old, this is the old policy, because using the old policy, if you give it a question, it will come up with a group of these outputs, and then optimize the policy model pi theta. This is the new, we want to get the new policy by maximizing the following. This is the objective function it has. Okay, this is the objective function. This is what you have to understand. So this is the expectation. So you have this Q, you sample it from here. So this is the output. Okay, this output is, so you can see this same whatever they wrote over here. Oops. So whatever they wrote over here till here. So this is the equation that is saying it in equation sense. The first line of the equation. This is in words. This is the equation. So this is expectation. So you have this Q and you take it. Let's suppose you have P of Q. You take it from some questions from some this distribution, and now you get these outputs. You get these outputs from this pi old. That's what they said. They said for each question q, because these questions are sampled from some q, okay, and it outputs a group of this from the old. So it outputs this group oi. So how many groups till g? That's what they said. O1 to OG. So that's what it's writing over here. So I am teaching you how do you read mathematics like English. They have written English over here at the bottom. They have written it the same thing in mathematics. So they basically what they want to do is they want to optimize this. So this is the older model. So they take older model, okay, and from this they output this. So how do they do it? So they minimize this. Okay, this is the policy what they get from outside, and they have this AI factor. So AI factor basically is how much better is it. So if it's if you give it better, it will be a higher number. Okay, and then this is called a clipping. So this is a separate paper on clip also. Okay, I won't go into this more. And this is the regularization that I think I taught you regularization. So this is actually KL divergence. This is called KL divergence. What it does is, so it will sometimes what's called as hacking. It will find hack techniques. So if you have to optimize things, it will do something. So you have to see it does not go out of the distribution. So let's suppose if you gave something and it generated something like good, and good was actually considered the very good answer. So it was considered like, oh, this is actually good response from that. It will give it higher reward. But the problem is it actually did not learn it. It should learn distribution. So what we did here is this KL divergence basically tells you how much two distributions differ. We'll go on these. We'll learn about these concepts. But here, what I can tell you, so they are optimizing this. Okay. So what they do is, but in order or in this optimization, what can happen is, so model can somehow learn to hack it. So it can do something else. It can totally change the distribution. And it will maybe give the better reward. So in order to save from that, so in order to somehow navigate that, they added this term. So in which we have the scale divergence, which sort of takes care of that you should not too much shift from the distribution. Okay, and these are hyperparameters. This beta is a hyperparameter, and this epsilon is a hyperparameter. Okay, you clip these values in a certain range. That's why this clip is for. And then there is this AI also. So AI also they have defined. So this is AI over here. This is how they calculate AI. You have this Ri mean of these R1, R2 and everything, and then you have this standard deviation of these things. Okay, so this will maybe once we go to clip, I think you at least got the reward. So what they do is they give the old model and based on that they get the output. Okay, if that output from the old model was good, they have somehow this AI is there a coefficient by which they multiply it, and then they take minimum of these two. Either you clip or you find how good this old model was with respect to the new and find the minimum among those. Okay, that is the reward function they are making. In order to see that it should not hack, they added this term divergence, so that you should not diverge too much from the distribution or in distribution. This is what they use. This is the core equation. So here what we can do is you can take a screenshot of the equation and maybe with this technique as well. And by now you should paste it over here. So cold start, I think I'll put it here, and then I'll have to again maybe reorganize these certain things, and then we'll see this reward modeling. If you can see, the reward is the source of the training signal which decides the optimal direction of the RL. To train DeepSeek R0, we adopted a rule-based reward system, which I just said that there is a rule that mainly consists of two types of rewards. Accuracy rewards. The accuracy reward model evaluates whether the response is correct, if is it accurate or not. For example, in the case of math problem, we determine the result, which I said you have to find is the result correct at the end. The model is required to provide the final answer in a specified format. If it is that, it will get more reward for the accuracy. Enabling readable rule-based verification for correctness. Similarly, like lead code problems, you will give the test cases. So test, if it runs on test cases, it will get more accuracy reward. Then the second thing is format reward. In addition to the accuracy reward model, we employ a format reward. So in these tags, it will think. You have these think tags. Model enforces the model to put it in thinking process. So it will initially think that I showed you. So chain of thoughts or think. So which this DeepSeek. If you see, this is that thinking process. So this is under that think tag. And after thinking, it is giving this answer. That's what it's mentioning here. Format reward is how good you format. In addition to accuracy, we employ the format reward and this, and we do not apply the outcome or the process neural reward modeling in this 0 because we find the neural reward model may suffer from reward hacking. That's what I said. In large scale, reward hacking basically means somehow it will get the better reward, but it will not perform good. A reinforcement learning process and retains the reward model needs additional training resource, and it complicates the whole training. And then they are saying what is the template, which we already went through. To train DeepSeek R, we begin with design a straightforward template that guides the base model to adhere to our specified instructions as depicted in the table 1. So they have a table 1 over here. This is table 2. and this is the table 1. A conversation between user and assistant. The user asks a question and then assistant solves it. The assistant first thinks about reasoning process in the mind and then provides the user with the answer. The reasoning process and the answer are enclosed with this. So this is what they are saying. To train this, we begin with design a step-out template that guides the base model to adhere to our specific instructions. Activity of this template requires DeepSeek to produce a reasoning process first, which it just did. We set the example of binomial theorem. Avoiding any context-specific bias such as mandatory reflexive reasoning or prompting a particular problem-solving strategies to ensure that we can accurately observe the model's natural progression during the reinforcement. That's why they did it. Okay, and then they are speaking about performance, and then self-evolution, and then there is the aha moment. So in aha moment, what they say, so it sometimes rethinks again. So this is good. So I think this is not worth reading. This performance, you can again see it repeating things. So self-evaluation process, the self-evaluation process of DeepSeek Zero is fascinating. How RL can drive a model to improve its reasoning capabilities. Autonomy. By initiating RL directly from the base model, we closely monitor the model's progression without any influence of the external SFT. This approach provides a clear view of how model evolves over time, particularly in the terms of its ability to handle complex reasoning tasks, as depicted by this. Okay, the average response length of the depicted on training doing this, DeepSeek Zero naturally learns to solve reasoning tasks with more thinking. Okay, so this is basically the time steps and average length per response. Okay, so you can see as steps increase, the average length per response also increase. That is, it was thinking more before giving the answer. This improvement is not a result of excellent adjustments because they have not actually adjusted. It is purely from the RL. DeepSeek R naturally acquires this ability to solve complex reasoning tasks by leveraging extended time compute. This computer ranges from generating hundreds of thousands of reasoning tokens, allowing the model to explore and refine its thought process in a greater depth because it thinks more. As it also, if you see, it thought a lot of things over here. So is it right? Then it also tried to verify the answer, checked it. One of the model's remarkable aspects of this evolution is sophisticated behavior. As the test time component increases, behavior says reflection because it reflects on its thoughts because it says, okay, let's test it. That's reflection. When the model reveals and reevaluates its previous step, okay, that's what it learned. Here we saw that in the binomial theorem also. Are you following this? Am I going too fast? How many of you following this? Yes, up so okay. Okay, so these behaviors are not programmed, but instead emerge as a natural property. They emerged. That's why it's called emergent behavior. And this spontaneous development enhances these capabilities, enabling the tackle more gen tasks without greater accuracy. So this was this, and the aha moment is this. It sometimes auto-corrects itself also. A particularly intriguing phenomenon observed during the training of DeepSeek R1 is occurrence of aha moment. This moment, as illustrated in the table, table 3 has this moment. So C2 over here. If a is greater than 1, then find the sum of this. So it'll think. So in here it'll have this. Wait. You can see it. Let us reevaluate this step by identifying if the correct sum can we start with this equation. Okay, it's reevaluates again. That's why they call it aha moment. Occurs an intermediate version of model during the phase DeepSeek learns to allocate more thinking time to a problem by reevaluating its initial approach. So whatever it did, it tries to see, okay, is it wrong or right? So let me think once more. Let me check it. This behavior is not only a testament to the model's growing reasoning ability, but also captivating examples of how reinforcement can lead to unexpected and sophisticated outcomes. This moment is not only an aha moment for the model, but also for the researchers observing its behavior. It underscores the power and beauty of RL. Rather than actually teaching the model on how to solve a problem, we provide it with the right incentives, and it automatically develops advanced problem-solving strategies. The aha moment serves as a powerful reminder for the potential RL unlock new levels of intelligence in artificial systems, paving the way for more automation and adaptive model in the future. Okay, this is what. And drawbacks. Although this exhibits strong reasoning capability, the automation accelerates powerful reasoning behavior. It faces several issues. For instance, struggle with challenges like poor readability. Okay, to make reasoning process more readable and share them with open community, we did this. So DeepSeek R1 learning with inspired by the promising results from this, two natural questions arise. Can reasoning performance be further improved or converge accelerated by incorporating small amount of high quality data at cold start? How can we train user-friendly model that not only produce clear and coherent chain of thought, but also demonstrate strong general capabilities? To address these questions, we design a pipeline to train, and this is the pipeline. Okay, and reasoning oriented reinforcement, and then rejection sampling. So whatever we wrote over here, so they are now explaining this process. So these steps they are explaining. Okay, and the non-reasoning data reinforcement learning all scenarios, then they do distillation, and these are the experiments they performed, and these are benchmarks, and then they have shown different things, different scores. Okay, I think now these 4-5 steps are explained. Okay, I think I'll conclude the paper here because we're taking too much time. So how many of you at least have a good idea of DeepSeek R1 now? What it does? At least the pipeline. Questions? Do you have questions?